Welcome to No Human Left Behind, AI the podcast. In today's episode, we give you knowledge representation and reasoning in AI.
Welcome back, everyone. We're diving into something pretty big today. Knowledge representation and reasoning in AI. It's basically, how do we make computers, smart? Like, smart enough to use knowledge the way we do?
Yeah, that's the core question, isn't it?
And we've got some interesting source material, a whole lesson from an AI course. So we're going back to basics to really get this whole knowledge thing figured out.
And it's funny, when we talk about smart computers, we're really talking about their ability to use knowledge.
Right.
To reason, to make decisions, and solve those tricky problems. Just like humans, they need knowledge to function in a way we'd call intelligent.
That's so true. We don't even think about how much knowledge we use every day. But computers, well, they don't think like us at all. So how do we even begin to, encode information for them to use? It's almost like translating how we understand things into something they can process.
It's a huge challenge. That's where this idea of knowledge representation comes in.
Okay, yeah, I've heard that term, but
It's about finding formal ways to represent information, facts, relationships, even rules. And putting them in a way computers can work with. It's like creating a language just for AI.
a whole new language. Wow.
And just like with human languages, there are lots of ways to do it. We call them schemes in AI, and they all have strengths, weaknesses, depends on the problem you're trying to solve.
So there's no one right way. Makes sense, I guess. But where do you even start with something this complex? What are the building blocks of this AI language?
Believe it or not, we start with good old logic, the kind you might have learned in school. Propositional logic, to be precise. It's about true-false statements.
Oh, right. Propositional logic.
Yeah, so we use symbols and these connectors to make a kind of shorthand that computers can get. Simple example, it's raining. Could be the symbol P.
So we're turning basic facts into a form a computer can grasp.
Exactly.
But how do we go from just stating facts to showing how things relate? Because the world's not just a list of true or false stuff, right?
Right. You need more power. That's where first-order logic comes in. FOL. It's like propositional logic, but supercharged.
Yeah.
Now we can represent relationships between things.
Oh, interesting.
So all humans are mortal, that idea. FOL lets us express that kind of rule.
So we're going from basic facts to encoding rules about how things work. That's cool.
It is. And those rules, they let AI go beyond just storing info. Now it can start to reason with it.
Whoa, okay. But logic, that's not all our brains do, right? It's more like a jumbled web of ideas, always changing. How does AI handle that kind of knowledge?
You're right. It's messy. That's where we get to things like semantic networks. Think of a giant mind map. Each node is a concept. Links show how they're related. Like bird connected to robin with an is-a-link.
So it's about showing those connections visually.
Exactly. And then there are frames. Imagine a template for an object, like a car frame, has slots for make, model, year, all that. Helps organize the info.
Frames are like pre-built knowledge organizers then.
That's a good way to put it. But here's the thing. The real world isn't always neat and tidy. How do we deal with the fact that things aren't always just true or false? Uncertainty's everywhere.
Yeah, true. How does AI deal with that? Not just thinking logically, but dealing with the messiness of real life.
That's where it gets even more interesting, because uncertainty is everywhere in the real world. Thankfully, AI's got ways to work with it.
Okay, so how does it do that?
One way is probability theory. Gives us this math framework to represent those uncertain things. Like, it's not will it rain, but there's a 70% chance.
So it's not just black and white anymore.
Right. And then there are Bayesian networks. Remember those mind maps? Now imagine each connection has a probability on it. They model complex systems, lots of variables.
Bayesian.
No.
And that sounds intense, but powerful too, right? AI is constantly updating what it knows.
Exactly. And then there's fuzzy logic that deals with, fuzzy things. Like how tall is someone? Not a yes-no. It's degrees of truth.
So AI can handle those vague concepts too. We've got logic, networks, probability, fuzziness. It's like a whole toolbox. But once we have all this knowledge organized, how do we make AI use it?
That's the next big step. We go from representing knowledge to reasoning with it. One of the most classic ways. Rule-based systems.
Rules, okay? Like what?
Think if-then statements. Like, if it's raining, then take an umbrella.
Sounds simple, but I bet it can get more complex.
Oh, absolutely. This leads to expert systems, designed to mimic human experts in specific fields.
Whoa, like an AI doctor or lawyer?
Exactly. One of the first ones back in the 70s was called MYCIN, It helped diagnose bacterial infections.
Wow, AI was doing that back then. That's incredible.
Right.
But what about AI actually acting in the world, not just giving advice? Robots and stuff, making decisions in real time.
That's where planning and decision-making come in, particularly under all that uncertainty.
Okay, I'm all ears. Tell me more.
One of the big tools there is something called Markov Decision Processes, or MDPs. It's a way to model these tricky decision problems, find the best actions to take.
Markov. That sounds familiar, but I don't remember why.
It's all about predicting what's going to happen next. MDPs help AI break things down into steps and figure out the best move at each step.
So it's like planning, but knowing there might be detours along the way. But how does AI learn to make the best decisions?
That takes us to reinforcement learning, RL, learning by experience, just like we do. Imagine an AI trying stuff, getting feedback, good or bad. Over time, it learns what works.
So it's trial and error, but for AI. Fascinating. It feels like we've gone from encoding basic facts to building systems that can reason and learn.
And it's pretty incredible how it all comes together, isn't it? But it does raise another question. We've talked about representing knowledge and about learning from data. Can those two things work together?
That's a great question. I mean, data is powerful, but having some knowledge already, wouldn't that make learning faster, more efficient?
Absolutely. And it's a hot research topic right now. Using knowledge to guide learning, make those AI systems even better.
So it's not just about crunching numbers anymore. We're adding back in that human element, that reasoning.
Exactly. Finding that sweet spot between the two. But of course, it's not all easy. There are some serious bumps in the road when you're trying to build truly intelligent AI.
Oh, I bet. What kind of challenges?
One of the biggest is something we call the knowledge acquisition bottleneck.
Bottleneck. That doesn't sound good. What does it mean?
It means getting all the knowledge we need and putting it into a form AI can use is really hard. Think about everything you know about the world, all that common sense stuff we take for granted. Writing it all down for a computer is almost impossible.
It's like trying to write down everything on the internet on one tiny sticky note.
Pretty much. And then there's common sense reasoning itself.
Yeah.
Humans just get certain things, but teaching that to AI, incredibly tough.
Like those CAPI-TCHA tests online, telling cards from bicycles. We do it instantly, but for AI, it's hard. And I bet all this reasoning takes a ton of computer power, too.
You're right. Even with all the advances we've made, there are still limits. It's a constant balancing act.
So where's all this going? What's the big goal with knowledge representation and reasoning?
The ultimate dream. AI that's more integrated, more human-like in how it understands the world. AI that learns faster, handles uncertainty better, and can apply its knowledge to new situations just like we do.
So closing the gap between how we think and how AI operates, that's a huge goal. What are the most promising areas of research right now?
There are a few exciting ones. One is called neurosymbolic AI, combining deep learning, which is all about data, with symbolic reasoning, like we've been talking about.
So the best of both worlds.
Exactly. We're also seeing progress on AI that deals with uncertainty better, learns from less data, and even shows some basic common sense reasoning.
It sounds like we're on the edge of something big. AI is getting smarter all the time.
It really is an exciting time to be working in this field. The possibilities seem endless.
This has been amazing. We've covered so much, from basic logic to those big challenges of common sense and stuff. And it feels like we've only just scratched the surface of what's possible with AI.
You know, before we got into all the challenges and stuff, we were talking about how to organize the knowledge we give to AI.
Right. Like, it's not enough to just have a ton of information.
Exactly. It needs to be structured. Think of it like, you know, a huge library, but there's no Dewey Decimal System, no way to find anything.
Oh, totally. Like having all the ingredients for a recipe, but no instructions. Just a mess of stuff.
All right.
So how do we organize all that knowledge for AI?
Well, that's where things like knowledge graphs and ontologies come in. They're like the tools we use to create a framework for all that knowledge, something AI systems can actually use.
Okay, knowledge graphs and ontologies. Those sound kind of complicated.
They're powerful, that's for sure.
Yeah.
Let's start with knowledge graphs. Imagine like a giant web of nodes, kind of like those semantic networks we talked about, but much bigger. Each node is a concept, an object, a thing in the world.
Okay, and the links between them are the relationships.
Exactly. So you could have a knowledge graph about movies,
Yeah.
nodes for directors, actors, films, genres, all connected to show how they relate.
Oh, I get it. So, like, you could have a link saying directed by connecting a director to their films.
Exactly. And you could ask, what movies did Steven Spielberg direct? And the graph would tell you. It's like a searchable database, but everything's connected in a meaningful way.
So it's not just storing facts, it's showing how those facts relate to each other. Pretty powerful stuff.
It is. They can have millions, even billions of entities and relationships in them, capturing a ton of human knowledge. But you also asked about ontologies. Think of those as the blueprints for building the knowledge graphs.
Blueprints, okay. So they tell you how to build the graph.
Yeah, they define the structure, the rules. It's like the grammar and vocab of our knowledge representation language. They say what kinds of things exist, what properties they have, and how those properties relate.
So if the knowledge graph is the map, the ontology is the legend.
Perfect analogy. So an ontology for movies would define what it means to be a director, an actor, a film, and all that. What properties they have.
Makes sense. It's all about making sure the AI is understanding things correctly, right? Not getting confused by different meanings.
Exactly. Without a clear ontology, your knowledge graph gets messy fast. And the cool thing is, it's both human readable and machine readable. We can understand it, and the AI can use it.
It's like a bridge between how we think and how machines think. But building these things sounds like a huge job. Who's doing all that work?
Well, there are definitely teams of experts involved, but thankfully we're not doing it all by hand anymore. We're using things like natural language processing and machine learning to automate some of it.
So we're teaching AI to build its own knowledge base. Wow.
It's pretty cool, but it's still tricky, making sure the info is accurate, dealing with the ambiguity. It's an ongoing challenge.
So it's like this never-ending quest for knowledge.
Kind of, yeah. But let's say we do have this perfect knowledge graph with a good ontology and accurate info. What then? How does the AI actually use it?
Yeah, good point. It's one thing to have all this knowledge organized, but how does it actually lead to, intelligent behavior?
That's where we get to reasoning and inference. We've got this amazing structure, now we need to put it to work. Reasoning is like the engine that makes intelligent behavior possible, drawing conclusions, making decisions, solving problems, all based on the knowledge we've represented.
Okay, so fire up that engine. How does AI go from connected nodes and relationships to actually doing something?
There are a few different types of reasoning AI can use. One of the most basic is deductive reasoning.
Oh, yeah, deductive reasoning. I remember that from, philosophy class or something.
It's about drawing logically certain conclusions from a set of premises. Like, if we know all humans are mortal and we know Socrates is a human, then we can deduce Socrates is mortal.
Right, it's like a logic puzzle.
Exactly. Deductive reasoning is all about following the rules of logic to get to a guaranteed truth. It's a big part of AI systems that work with formal logic.
But the real world isn't always so neat and tidy. What about when we don't have all the information? When we have to, make an educated guess based on what we do know?
That's where inductive reasoning comes in. This was all about drawing general conclusions from specific observations. It's how we do science. And it's a cornerstone of machine learning.
So instead of having a hard and fast rule, we're looking for patterns in the data and making generalizations.
You got it. Inductive reasoning lets AI make predictions even with incomplete knowledge. It's how AI learns to recognize patterns, classify objects, and all that.
So we've got deductive reasoning for when we have clear rules and inductive reasoning for when we have to fill in the gaps. Are there any other types of reasoning?
There's one more called abductive reasoning. It's about finding the best possible explanation for something, even if we can't be 100% certain.
Oh, like when a doctor is diagnosing a patient based on their symptoms.
Exactly. Abductive reasoning is all about coming up with the most plausible hypothesis, even if we can't prove it definitively. It's used a lot in medical diagnosis, science, even just everyday problem solving.
So AI has this whole toolkit of reasoning methods. That's pretty amazing. But how do we actually implement these different types of reasoning in AI systems?
Well, that's where inference engines come into play. Think of them as the brains of those rule-based systems we talked about. They take the knowledge we've represented, apply the rules of logic and reasoning, and then, bam, they spit out new conclusions or answers to questions.
So it's like having a mini Sherlock Holmes inside the AI, constantly analyzing and making connections.
That's a great way to put it. They can work in different ways, too. Sometimes they use forward chaining, starting with facts and applying rules to see what new stuff they can figure out. Other times it's backward chaining, starting with a goal and working backward to figure out what facts would lead to that goal.
So they can either build knowledge up from the bottom or work backward from a desired outcome.
Exactly. Very versatile, those inference engines. But of course, things get tricky when information is incomplete or inconsistent.
Right. What happens when our AI Sherlock hits a dead end?
That's a huge challenge. The real world's messy, so we need ways to deal with that. Things like default reasoning, to make assumptions when info's missing, and belief revision, to update beliefs when new evidence comes in, even if it contradicts what the AI thought before.
So it's about teaching AI to be okay with not knowing everything, with things changing. That's pretty tough.
It is. But we've come a long way. We've talked about knowledge graphs, ontologies, all sorts of reasoning, and those powerful inference engines. It's clear that representing and reasoning with knowledge is super important for making truly intelligent AI. But now the question is, how do we take all this and make it work in the real world?
Yeah, it's one thing to have AI that can think and reason, but what about AI that can actually do things, like robots and stuff?
Right, that takes us to the world of robotics and embodied AI, where intelligence takes physical form and interacts with the world around us.
So robots that can move around, perceive things, interact with their environment, this is where it starts to sound like science fiction.
It is pretty amazing.
Yeah.
But it all starts with giving those robots a way to understand the physical world.
Okay, I'm definitely intrigued. Tell me more. How do we give robots the knowledge they need to operate in this complex, messy world of ours? So we're talking robots that aren't just moving around randomly, but actually understanding their environment. That's a whole other level. How do we even start giving them that kind of knowledge?
It all begins with, well, the basics. Space and time. Robots need to know where they are, how to see the objects around them, and get that things can change. It's like building a mental map for them.
So it's more than just recognizing, like, that's a chair. It's knowing where that chair is in relation to the robot itself.
Exactly. And that kind of spatial reasoning, temporal reasoning too, it's crucial for just about everything they do. Like, think about navigating a room. The robot can't just bump into stuff. It needs to know how to move around.
We take that for granted, don't we? Knowing where things are, how to move without running into them. But for a robot, that's a ton of complex math and programming. Are there specific techniques that help them with this mental map building?
One of the big ones is called SLAM. It stands for Simultaneous Localization and Mapping.
SLAM. Okay, that sounds intense.
It is. It's like giving the robot a compass, a map, and a sense of direction all at once. It uses sensors, like cameras or lasers, to gather info about its surroundings.
So it's constantly scanning its environment.
Yeah, and then it uses that information to build the map and keep track of where it is on that map all at the same time.
So it's like exploring a new city, but you're drawing the map as you go. That's wild.
Great analogy.
Yeah.
And a lot of these SLAM algorithms, they use probability too, to deal with uncertainty. Because sensors aren't perfect and the world's unpredictable.
Right, because a sensor might give a slightly wrong reading, or something could have moved since the robot last saw it. So it's making these educated guesses just like we do.
Exactly. It's a perfect example of how those core ideas we talked about, knowledge representation and reasoning, are actually used in the real world. But SLAM is just one part of it. Once the robot has a good map, it needs to be able to plan what to do next, achieve its goals,
Right, because knowing where things are is cool, but actually doing something useful with that knowledge is a whole other challenge. So how do we go from understanding the environment to, like, taking actions in that environment?
That's where planning comes in. We use these symbolic representations of actions, their preconditions, and their effects, so the robot can reason about what will happen if it does something.
So it's like giving the robot instructions, but also the ability to think about those instructions and adapt them, not just blindly following orders, but understanding why it's doing something.
Exactly. Imagine a robot that needs to fetch a cup from the kitchen. We can break that down into smaller steps. Go into the kitchen, finding the cup, grabbing it, bringing it back. Each step has things that need to be true before it can happen and consequences after it happens.
So the robot needs to think about those things to figure out the right order of actions. Like, to grab the cup, it needs to be close enough to the cup, and its hand can't be full already.
Right. And what if it bumps into something on the way to the kitchen? It has to adjust its plan. It's all about this ability to reason about actions and to adapt to unexpected things.
Sounds like a lot of problem solving.
It is. And this is where things like reinforcement learning can be really helpful. Remember how we talked about AI agents learning from experience? Well, robots can do that too.
So they can learn from their mistakes.
Exactly. By trying things out and seeing what works, they can get better and better at achieving their goals. But we focused a lot on navigation and planning. What about interacting with objects? How does a robot go from seeing something to actually picking it up and, using it?
Yeah, that's a good point. It's one thing to map your surroundings, it's another to actually do something in those surroundings.
That's a huge part of what we call embodied AI, where intelligence is connected to the physical world. And it brings a whole new set of challenges. Robots need to understand object recognition, scene understanding, even physics, to interact with things effectively.
So it's not just, I see a cup. It's, I understand that this is a container, it can hold liquid, it has a handle, and it might break if I drop it.
You got it. It's about building a rich understanding of objects, not just what they look like, but what you can do with them, how they relate to other things. Their affordances, we call them.
So we're teaching robots to see the world not just as a bunch of shapes and colors, but as a collection of things they can interact with, each with their own properties and possibilities.
Exactly. It's combining perception, knowledge representation, and reasoning, all to enable this intelligent behavior in the real world. But the ultimate challenge, maybe, is getting robots to interact with us in a natural way. That's where human-robot interaction comes in, HRI.
HRI. That's where things get really interesting. Robots understanding our language, our intentions, maybe even our emotions.
It's a tough one, but researchers are making progress. We're seeing robots that can follow spoken commands, understand gestures, even have basic conversations.
So it's not just programming them with a bunch of pre-written responses. It's about them actually understanding what we mean.
Exactly. And it goes beyond the words and gestures themselves. It's about giving robots a model of how humans think. Our beliefs, desires, intentions. Building robots that can anticipate our needs, work with us, maybe even be companions.
That's taking knowledge representation and reasoning to a whole other level, applying it to the human mind itself.
It is. It's a huge challenge, but the potential benefits are enormous. Think about robots that can help us with everyday tasks, care for people, teach, even be creative collaborators.
It's a future where robots aren't just tools, but partners.
It is a future full of possibilities, but also ethical questions we need to think carefully about.
Wow, we've covered so much ground today. From logic to human-robot interaction, it's clear that knowledge representation and reasoning are at the heart of AI.
And we've just scratched the surface. This field is moving so fast. New discoveries are happening all the time.
It's both exciting and a little mind-boggling to think about where this could all lead.
It is. But trying to understand and create intelligence, that's got to be one of the most fascinating challenges out there.
Couldn't agree more. Well, that brings us to the end of our deep dive into knowledge representation and reasoning. We hope you've enjoyed it.
Definitely. Keep exploring. Who knows, maybe you'll be the one to make the next big breakthrough in AI.
And until next time, keep those AI curiosity circuits firing.